Okay, Algebra 1, we are going to cover the introduction to linear equations. So a linear equation is an equation whose graph produces a line. And the way that you can remember that is the word linear has the word line right in it. Okay? So a linear equation is an equation whose graph produces a line. So I've got three graphs here. Which one is a linear equation? Well, it is letter C. This is a curve, this is another curve, this is the only straight line. So a linear equation is going to produce a straight line. It says the equation x plus y equals 3 is an example of a linear equation. To graph it, let's complete the table below by finding the y values. Then we can plot them. So you guys have done this before. In order to find the y values, you'd have to move the x over to the other side. Our equation is going to read 3 minus x. So if we put negative 1 in here, we would get 3 minus a negative 1, which would be 4. If we put a 0 in, we'd get 3. If we put a 1 in, we'd get a 2. And if we put a 2 in, we'd get a 1. So if we plot these points, I'd have negative 1, positive 4, 0, 3, 1, 2, and 2, 1. So you can see that this would create a nice straight line across my graph. So it says let's mark more points and draw a line through them. So I could continue with this. Okay, and it says circle the ordered pairs that are on the line. So let's check. Negative 2, 5. Okay. 4, 1, 2, 3, 4, 2. Nope. 3, 0. 3, 0. 3, 0, yep. And now, can we see those? Okay. No, we really can't, but how can, it says it's not easy to tell from the graph whether some of the ordered pairs above are on the line. So once they get bigger, or if they're decimals, it becomes difficult. Like maybe we can check this one, 1.5 and positive 1.5. Yeah, that's probably on there. Okay, but it becomes more difficult. So, but we can, by all means, use an equation to see if the line or the points are on the line. The graph of an equation in two variables is the set of all of its solutions. Okay, so let's decide whether the following points are on the line. So this is my x, this is my y, and you guys have done this before where we're going to put the 4 in for the x, the 15 in for the y. 2 times 4 is 8. 15 minus 7 is 8. So is this on the line? Yes. Remember again, x, y. So 2 times a negative 1 equals 6 minus 7. 2 times a negative 1 is a negative 2. 6 minus 7 is a negative 1. So this is not true. So no, that point is not on our line. So this next one, 2 times negative 8.6 equals negative 10.2 minus 7. So 8.6 times 2, that would give me 17.2, negative 17.2. And if I take negative 10 and I take away 7 more, it gives me a negative 17.2. So yes, this one is on the line, or does make the equation true. So if it makes the equation true, like these two, it is on the line. If it doesn't make the equation true, it's not on the line. Okay, so it says it's easy to recognize a linear equation graphically. Yep, obvious if we put it on a graph and it comes out straight line, it's usually a linear equation, but we also must be able to do it symbolically. So there's a couple things to look for. So these are linear and these are nonlinear. So I'm going to point out some things that make them nonlinear. Like you cannot have exponents. So I'm just going to write over here x and y cannot have exponents. Okay. Other thing, it cannot be divided. It cannot be under a fraction. So x or y cannot be dividing, or in the denominator, however you want to think about that. X and y cannot be multiplied. X and y cannot be multiplied together. Cannot be under the square root. And it cannot be in an exponent. Be, I would say, used as, sorry, I'm going to run out of room, exponent. Okay, so those are the main things. I kind of circled them in each problem, and that it might just be one variable, but it doesn't matter. X or y cannot be used. It might produce a function, but it's not going to be linear, so nonlinear equations. So you are going to notice that our equations are going to look different. X can be in the numerator. X can be in a parentheses, and we can multiply numbers times x or y, but we cannot multiply them by each other. And you can have this, y equals x and x equals 8. So those are all examples of linear equations. So in conclusion, the linear equations must have variables. We need an x and y in there. And the variables may only have coefficients. So coefficient is a number in front of the variable. So let's circle the linear equations below. So sometimes it's easier to rule out the ones that break the rules. So for example, this one breaks the rules. So cross that one out. What's another one that breaks the rules? This one breaks the rules. This one breaks the rules because they're being multiplied. This one, I know that it looks tricky, but really if you get x by itself, it would be x equals 7 halves, and that's okay. We're going to talk about this y equals 0 one. If that is y equals 0, that means that for every x, y is 0. And so it's going to cross the y-axis at 0. It's going to cross right here. It's going to look like this. And that is a function. Okay? I'm just trying to think if there's any other ones I'm just peeking through. It's okay to divide. Okay. Oh, I'm going to pause this one. Y equals 0. That means every y equals 0 crosses the y at 0. Yeah, that one should be good. Okay, so we can also recognize linear relationships by looking at the tables. The table below shows 3 solutions to a linear equation. Prove this relationship is linear by finding the rate of change or the slope between its ordered pairs. So we just did this in our last one. And so what you have to do is find the rate of change, the slope between these 3 pairs. So basically you're going to find the rate of change between these 3. So they're going to have you use the slope formula. M equals y2 minus y1 over x2 minus x1, x1, y1, x2, y2. So this is going to be 1 minus a negative 5 and 1 minus 13. 1 minus a negative 5 gives us 6. 1 minus 13 gives you a negative 12, so that reduces to a negative 1/2. Follow through on these ones, x2, y2, or x1, y1, x2, y2. So this is going to be a negative 21 minus 13 and 12 minus a negative 5. When you have a negative 21 minus a negative 13, it ends up plus a negative, so then you end up with a negative 34. And on the bottom, these end up being added, so then you get a 17. And this turns out to be a 2/1. Okay. So these are not the same so far. Megan, just double checking. I always like to double check y, x's, y. Oh, did I mess this up? I did. See, I thought maybe I did something wrong. Okay, look, I'm gonna go back to this one. I put my y with my x. Sorry, guys. 1 minus 13, that would give me a negative 12. And then 1 minus a negative 5, and that'd give me a 6. Goodness, goodness, goodness. So negative 12 over 6 does give you a negative 2. So far they do match. I apologize. x1, y1, x2, y2. This is going to be a negative 21 minus 1 over 12 minus 1. Negative 21 minus 1. I'm nervous of making a mistake. Negative 22, and 12 minus 1 is 11. So this also reduces to negative 2. So the rate of change was the same on all of them. Now the other way to do this, I like to look at the table. And if this is consistent, it doesn't always work because your table has to be consistent. So 13 to 1 is a negative 12. And then 1 to 21, oh, maybe this won't work for this one. This is an 11. And then this is going to be negative 5, so negative 6. And 1 minus 21 gives you a 22. So what ends up happening here is the change is this one went up 6, down 12. So it was 12 over 6 and 22 over 11, which turns out to be the same thing as 2 over 1. So sometimes you can just use your graph or your table to look at that. So I think that's what it's going to show you here. It says when one value grows by equal differences, it's easy to recognize relationships. Find the linear relationships. So we did it kind of longhand here, and we're going to take the shorter cuts here. So from 7 to 10, it went up 3. From 10 to 12, it went up 2. From 12 to 16, it went up 4. So let's look what happens over here. It went up 1, it went up 1, it went up 1. So these were consistent, but these were not. So this is not linear. Okay, they have to go by equal differences. So this one from negative 1 to 4 was a positive 5. From 4 to 9 is a positive 5. From 9 to 14 is a positive 5. From 3 to 4, it's 1. From 4 to 5, it's 1. From 5 to 6 is 1. These all differed by 1. These all differed by 5. So it's a yes. 3 to 4, it's 1. 4 to 6 is 2. 6 to 9 is 3. So that one, they're not the same. Let's look at these. 2 to 4 is 2. 4 to 6 is 2. 6 to 8 is 2. So this one's a no because of this right here. 20 to 17 is a negative 3. 17 to 14 is a negative 3. 14 to 11 is a negative 3. These ones all went up by 3. Okay, these are consistent. These are consistent. It's a yes. Last one here went up by 1, up by 2, up by 4. Up by 1, up by 1, up by 1. So this is a no because of this, because this was not consistent. So they have to be consistent. Equal differences is a big deal. Okay, the last little part. It says, let's decide which situations are linear. So remember, linear also means like a constant. Okay, so Jack makes $14 per hour. Does this rate change? Nope, the rate stays the same. So yes, it's linear. I get a $1,500 raise in salary. So is this linear? Is it consistent? Each year it says, so that means every year it's going to keep happening. So this would mean it's linear. The baby grew fast at first and then slowly. So this, would it be a straight line going up? Like if we were graphing this, would it be a straight line like this? Nope. The baby grew fast at first and then it kind of leveled off. So this is not linear. The number of cells doubled every hour. So is this change constant if it's doubling every hour? Nope. Because it's going to increase by a different amount every time. Each year, I get a 5% raise in salary. So this one is kind of tricky. A 5% raise means that it's multiplying by a 0.05. So the salary would be multiplied by 0.05. So this one you can think of it different ways. So it depends if this number, x, changes every year, or if you always have the same x. So I'm going to say if you would think of it like this, then it would be a yes. My company is losing $1,000 every month. So it's consistent every month. So we're going to say yes. Now, if this one, I'm going to go back to the salary one. If we were thinking about it as the x changed every year, then this would be a no, because eventually you'd be making, it would increase more than it did the first year. But we'll just kind of go depending on how you interpret that question. Okay? So that is linear. It's constant change, straight line, and we're watching out for some of those tells in the equations.